The title running Linux on Windows says that the targeted audience are Windows users who might want to use and practice on Linux. Our past training statistics show that over 67% of participants are using Windows, and around 15% are using Mac, and a small percentage of people were Linux users. Given that our national supercomputers and the clouds are running Linux, it is essential to have access to Linux and to become good at it. Here's an outline of today's talk. What is and why Windows subsystem for Linux, or WSL? What do you need to have it? And best practices, and I'll spend some time on getting started to play with Windows and Linux together. And moving on, I'll show you some examples of using Linux on Windows for developing and testing some code. And lastly, I'm going to show you briefly how to take the Linux distro of your favorite choice running on your Windows subsystems and take it with you and use it somewhere else, for example, on the cluster. What is WSL? This diagram, based on the compiled information from the internet, including Microsoft's website, it depicts the architecture of modern Windows, or the latest Windows 11. The core part of a Windows runs on the top of a hypervisor, also known as a Type 1 hypervisor, which abstracts the interactions with the hardware and enables and facilitates the virtualization technology. And one may think of Windows as a whole includes the hypervisors as well. Windows subsystem for Linux, or WSL, is a subsystem isolated from a Windows, allowing the execution of a Linux inside. With WSL, one can run one or several Linux operating system inside on Windows. So why WSL, or the benefits? Well, one can do serious development work on Linux while still enjoying the features of Windows for day-to-day uses. The Windows subsystem for Linux is based on the virtualization technology, and each Linux runs as a virtual machine, but with a very little overhead compared to others. And one can develop and debug your code on WSL before you move to clusters. And it is always good to have a toolbox handy, and so you can work anywhere without the internet. And also, you can try and run several Linux distributions at the same time. So this allows advanced users to explore more possibilities. So if you haven't had the Linux on Windows, and here's what you need to do. You need to have a Windows 11, and you need to have 8 gigabytes of RAM and 50 gigabytes of storage for the Linux distro. Just make sure you have enough resources. And any recent laptops or desktops with a minimum of 16 gig of RAM, enough disk space should meet the minimum requirements. So you can go check settings, the systems about to see the information about your system. And, and of course, you need the internet connection, so you can install Linux on the go. Here's a few steps to enable WSL on Windows. We have video recordings made by SharkNet staff all set things up, available on SharkNet the YouTube channel at youtube.sharknet.ca. So all you need to do is fire up a PowerShell as administrators on Windows. And from command line, just type WSL install. And then just in a few seconds or a few moments, it should be installed smoothly with Windows 11. And then you can type command WSL --list -online. --online, you will see a list of available different Linux flavors for Windows subsystem. And then you can pick and choose. In the example here shown on the slide, I'm installing Debian. So you type WSL --install and Debian. And in a little while, the live bare metal Linux operating system, Linux distribution Debian will be installed on your Windows. And for those of you who want a little bit more fine-grained controls, here's a list of pointers. We call it advanced setting configurations in WSL. Just keeping in mind, there are two settings. One is for the particular specific Linux distribution. And this is set inside the Linux itself in the /etc and the file wsl.conf. And it controls auto mount, UID, GID, and other things. But if you're not a Linux user, advanced Linux user, you might just ignore it. It's already set by default. You don't need to worry about that. And there's a global setting. This is a set on Windows. For example, someone might want to give a certain amount of resources dedicated to WSL. For example, you want to give a half or a quarter of the memory and the disk space to WSL. You can do that by specifying the details in a file WSL config in this path on the C drive. Users use this is the modern Windows set up for users. Okay, so these two controls, two-level controls. And also some notes and the limitations, as I just mentioned briefly, that one can run your own flavors of Linux at the same time, several. I showed an example here, Ubuntu, Debian, Fedora, and Alma Linux. By the way, all the national clusters, all the clusters are running Alma Linux. If you can give it a try and install the Alma Linux on your Windows and get yourself familiar with that. And each one runs its own kernel. And as of WSL version 2, 2025, all Linux distros, called VMs, running in WSL share the memory and the cores set for WSL. So it is not possible to set the memory size or the number of cores per distro. Okay. And also all the Linux VMs share the same network space, namespace, and NAT or network address translation is used. For those of you who want to have a more advanced settings, they have a different IP addresses for the Linux distro. It is possible, but it's not easy as of now. Okay, just a note. And here's a list of sources where you can find the more detailed information. The most authoritative one is the Microsoft website, how to install WSL, and some advanced settings also can be found on the Microsoft website as well. And also, here's a video recording made by my colleague Armstrong, leveraging the power of Linux on Windows with WSL, and highly recommended. Take a look at it in your spare time. Okay, best practices. Here is a list of things to get us started. In the next couple of minutes, I can just walk you through these tasks essential to the effective day-to-day use of Linux and Windows side by side. I'm going to show you how to share file systems, how to access file system from how to access a Windows file system from Linux, and how to access a Linux file system from Windows. And I'm going to mention some development tools like compilers, debuggers, and programming languages, libraries, and also miscellaneous packages highly recommended for Linux. For example, the tools to get access to the internet, to download the files, curl, wget, SSH to connect to remote hosts, and network file system, which useful, very useful if you have a network file system nearby that you want to mount some of the file system onto your Linux operating system. Yeah, you can do that. You should have that installed. Some other tools as well. Let me get to the command line. This is my Windows desktop, and I start a PowerShell. This is how I get it started. And if you type WSL command -list, sorry, -L-V, this will list the distributions, the Linux distribution installed on this machine. I have two installed already, Ubuntu and Debian. I have another one, Docker desktop. I'll mention that at the end of this talk. And as well, you can type the command WSL-list -online, and then you will see a list of available Linux distributions or flavors that you can try. For example, Alma Linux, as I just mentioned, we're running Alma Linux on all the national clusters. Debian, Fedora, SUSE, SUSE Linux, Oracle Linux, Ubuntu, and Arch Linux, and so on and so forth. I'm not going to go into the details of what if you want to say, for example, you want to install a Linux not listed here, for example, Gentoo. That'll be another topic, and you can ask a question at the end of the question. We can possibly answer the questions how. Okay, this is just shows the local and online available Linux distros. Okay, next I'm going to start the my distro Ubuntu. So WSL-D for distro Ubuntu. Now I'm in the Linux now, and as a matter of fact, I'm running a Linux on Windows, and I have a little program called the Neo Fetch, and it is a program that tells me what Linux distribution I'm running and operating system, the kernel, and other things, including the CPU and memory. Okay, and this tells me this is and also tells you this is Ubuntu. Now, if I type ls, this is a Linux command, and I only have one file there. Now, the question is, how do I access my Windows files? The first question, because I mentioned that I'm going to show you how to, three things I want to do, sharing file systems, development tools, and some other miscellaneous. Okay. Now, uh, if you type df to list the file systems, and you will see there are a number of file systems available, and in particular, you see this a C drive, which is a Windows file system, is mounted here. Okay, now how do I access to my Windows file system? I'm going to do, I'll make a symbolic link. I'm going to link, uh, the mount point is a mount C, and under C, I have a users, and users, under users, the BGE. By the way, starting from C, a users, the BGE, this is the file structure on Windows. And under my username, I have directory called the documents. And everybody has on Windows has a documents, has a downloads, pictures, and everything. So this is one of them. And then I just make a link. And now I have access to my documents folder. If I go inside and type ls, I see my desktop. I see the documents on my desktop. Now, let me just make another link. C users, my username, and the downloads. That's another link. I made another link, and I'll make a pictures as well. And these are the most commonly used directories on Windows. And videos and music. Okay, so I got enough. And these are all the Windows folders. Okay. For example, if I want to see what's in the downloads, and this I have some files already downloaded there, and what's in pictures, I don't have anything there. Oh, I have some screenshots there. And yeah, so this is how you can access your Windows files, file systems. So next, I'll see the development tools. As I mentioned, we need compilers and libraries. So, as a matter of fact, I already installed some of the packages, but I'm running Ubuntu, so I'm going to show you how to see what packages are available and needed. And I run apt and want to see GCC or GNU compilers. And then you can see a whole bunch of files are available. These are these are the available packages, and in particular, you will see different versions of GCC 14.13, and the libraries are available, and you can install them as you need it. Now, to install a package, or this is a Linux, this has to do with Linux or Linux specific, you do you need to be a super user and apt install and the username, for example, GCC 14, and that's the name you found it on this list. And you type the command and it will install the GCC 14 and dependent packages for you. Now, since I already got the GCC installed, let me just type the command GCC and the version and see what version is available. Now, I have a GCC 13 installed, and also I have a GCC Fortran installed as well, and G++. These is all installed. Um, and then I want to see what else I have installed. Apt list of packages and MPI. The MPI package, that's the libraries for developing a parallel program using MPI. So there's a list of packages available, but um, in particular, OpenMP, OpenMP, here example, there are two versions of MPIs available, most commonly used. One is OpenMPI, which is installed on all the national clusters, and the other version is MPISH, and that's another implementation. Let me just type OpenMPI, in particular OpenMPI. And you can see that the OpenMPI has been installed. If it indicates installed in a square brackets, it means that data package is already installed because I just want to save time and I installed that already. Okay, so if I type MPICC version, and you will see this is a MPI compiler based on the GNU compiler 13. Okay. As I mentioned, you want to install the another package called the cur. The cur, I think the cur is installed. Where is curl? No, curl is installed, and where is wget? And wget is also installed. These tools are commonly used for downloading files from the internet, which is handy for a command line. And also, I mentioned that I have an image. I mentioned the name called Image Magic, which is a package includes the tools for manipulating images, and supports more than 200 different formats of images. So if I do list image image magic, I think that's how it is spelled. Uh, well, I spelled it wrong, I guess. All right, yeah, I spelled it wrong. So Image Magic is being installed. And also, another one is the tuner. This is a file. This is a Windows file manager for Linux. It's like a file explorer on Windows. And this is one of the file managers, file explorers for Linux. So if I start this, and it will show the files manager, and then I can explore the files in it, different folders. Okay, this is a file manager tuner for Linux. Okay, so I've shown you the how to access the files on Windows file system. So basically, what I've done is I made symbolic links. Uh, I made a symbolic links to the Windows file system already mounted under MNT C. Okay. Uh, Next, let me see. I remove this link. This is a link to the file uh, to the files on the network. I'll remove link. I'll recreate it again. Uh, Sorry. Okay. Um, so now I have only access to the Windows folders. Now I want to have access to the files on the network, on my home network, or on the office network. And how do I do that? And here's the command. So I mounted this file over the internet, over the network. I need to mount this as a root. I mount the file system from this IP address, and in particular, the path to the folder I want to mount, and I mounted it on uh, the mount point on the local file system on this Linux. This is command. Okay, so I remounted the network file. Oh no, sorry, the network file system at this mount point. Now the next, I want to make a point, make a symlink, and I call it the net home. Now I could go to this folder. Oops, and then I see there are two folders in it, and also I can go to yes. Um, I run this file manager again. This is inside Linux. Inside Linux, go to home, and I see I have you see I have access to these folders, the file system, Windows file systems, and the new file system I just mounted. I call it net home. If I click that, and I see two folders, and click it again, I see more folders. Okay, so I'm showing you how to access Windows file system from inside the WSL, the Linux. Now, the next, I'm going to show you how to access file system from a Windows into the Linux in WSL. Now, this is a file manager. Sorry, this is a file explorer on Windows. Now I want to access the files on Linux. How do I do that? Now, after you start the Linux from Windows PowerShell window, and in your Windows PowerShell, you will see um, an icon here, Linux, and you toggle it and then see the list of Linux distros available installed on your Windows, and find the one you want to access. And in this case, Ubuntu. I click that, and it shows the file system. This is the file system on the Ubuntu. Now I want in particular access the files in my home account, and my user account is under home, and my username. I click that, and then I see this is my home account. Okay, in my home account, I see these files and documents, downloads, music, and that, and these is all Windows file system uh, as you can as just saw. I linked against. If I click documents, oops, I can see that. Oh, because this is on Windows. Yeah, you cannot. The Windows you cannot click the sim link, but uh, let's say these are all the links to the sim links to Windows file system. And on Windows, you cannot follow the sim links in Linux. But if I create a folder, let's say called the temp, and in temp, and I put let's say hello.txt, and hello. So I created a little file hello.txt in a folder temp, and then you should see there is a folder temp I just created, and this is the file I just created. So this example shows that you can also access a Linux file system from Windows. Okay. Okay, so back here, and then we're going to see that in the next few examples how to yeah, edit files. Now, once we have a Linux started on Windows, and then you have a Windows and the Linux side by side, and you have files stored both on Windows and the Linux, and then at some point you might want to edit the files. Say for example, using a Visual Studio Code, edit a file on Windows and edit a file on Linux. We can do that. For example, let me just start Visual Studio Code. The Visual Studio Code, and this runs on Windows. And I go to Files, and I try to open a file. Now, open a file. I want to open a file on Windows. Let's go to Desktop. Documents. Inside Documents. This is on Windows. I have a Markdown file. I open it up. This is my little Markdown file on Windows, and I can see the pre-rendered the content of this Markdown language. And then I try to open a file on Linux. Go to Home and go to my directory and go to the temp directory I just created. And there's a little hello world file, and click that and open. It says allowed, just open. So this is the content, and I can I can add something else, hello world, and save it. Now, if I go back here, go back to Linux and the temp and this file should being changed. So I should see hello world, that the world was what just I typed in the Visual Studio Code. Now, this only shows I'm using a Visual Studio Code, and I can edit a files on both Windows and the Linux. But the next I'm going to show you how to edit the files in Linux, but also to run things on Linux as well. Okay, so let's move on. Okay, some takeaways before I move on. And the Windows and your Linux on WSL live together, and you can access the Windows files from WSL or Linux, and vice versa. And then you can use the Visual Studio Code to edit Windows files and the Linux files at the same time. And at the next, I'm going to show you how you can do the development work on Linux through Visual Studio Code. Okay. Now, moving on, let's see how we can develop and test our code on Linux in WSL. I'm going to show you 3 examples. A C++ multi-threaded code, a parallel Fortran code with the support of MPI, and a parallel Julia code of using a distributed array. So first example is a multi-threaded code in C++. And I'm just adding 100 million random numbers in parallel using threads. The purpose of this example is to show developing and testing a threaded code on personal computers before you messing around the clusters. And the second is we can examine the performance of the threaded code and also being aware of some pitfalls of parallel processing. So the code, I'm just quickly putting the parallel code here. I do not expect that you understand or you remember this code immediately because there's quite busy code here. Let me just quickly go through them, and you can always examine or study the code after you get the copy of the slides. So this code is made by my colleague. Paul Brainy. This code demonstrates the use of threads to add array of random numbers all together. This code is written in C++. So first, we defined a data size, which is 100 million data size. And then we defined the data type, this is a variable. We define the data type as to be double. And then we define the two upper and lower and upper limits. And here in the main program here, and we declare a variable v as a vector or array. And then we allocate a space. This is statically allocated, 100 million. And then we generate data by calling a generator n. And the generator n is calling a random device to generate 100 million random numbers, all real, uniformly distributed between 0 and 99 in IEEE real format. And then we call the function accumulate to add the numbers in sequential order. And then we call a function again called reduce to add a number in parallel. And both accumulate and reduce are built-in functions. Accumulate is a serial function, and the reduce is a parallel function. This parallel function specifies the execution policy, which is in parallel and unsequential, uniquely unsequential. It takes the array, the beginning, and the end, and the type, and then it adds the numbers together in the arbitrary non-deterministic order, okay? And then we call the function chrono, or the timer, to time the execution time. We set a variable T1 and T2. These two are two ticks. And then T3, and then we subtract to get the duration for both the sequential and the parallel execution of that time. And then we just print it out. Okay, so basically that's what this code does. And everything inside the code is all building function. There's no user-defined function. So this is self-contained. Everything's here. Nothing specified elsewhere. Very simple code. Let me just show you the code here. The code. I'm gonna go to the code. The code is in my directory. Prepare for this talk. So this particular code, I call the name xsum.cpp. This is the actual code. So to compile this code, using the C++ compiler. And I specified the standard to use C++ 17. And with an option mark, M mark is a native. And then the name of this file, the C++ code. And I want to have an output name, give it to the same name. Otherwise, I will get an 8 out. And I will link against the thread building block at TBB. Oops. Okay, so the code is being compiled. And then next, I just run it. No. Before I run it, I'm going to mention that in this particular code, there is no way to specify the number of threads inside the C++ code. For details, if you want to ask a question, then we can answer that at the end of the presentation. Now, in order to use a different number for cores, I use a command called a task set. Task set with an option C and 0.0 this sets to use CPU 0. Okay, the CPU 0 that specifies the range of the CPU. If I this 0-0 means I'm gonna just use CPU 0, and then this program it will generate 100 million random numbers and then add them up and wait for a little while. And after it warms up, and it should spit the result. It takes a bit too long. Okay, now it takes a lot of time to generate the random numbers, and it took 1.5 seconds to add them up in a sequential order, and it took 1.57 seconds using a parallel. But since we're only using a one core, one thread, and essentially take the same number, the same amount of time. So next, I'm going to run using a 2 threads or 2 cores and see what we get.
Technically, that's 3 cores, 0, 1, 2.
Oh, sorry. Yeah. Thank you. Yeah, it takes a bit of time to generate the random numbers. Toward the end of the presentation, I'm going to show you how we do this on the cluster. It will take much less time, but just bear with me, and you will see some surprising results. Okay, yeah, and then you can see that the parallel execution it did take almost half of the time, the sequential time. The serial version accumulate, it takes 1.5, and the parallel version using 2 threads on 2 cores took about 0.7, so which is about a half of the time. But if you look at the result, they differ. This is very important. In a parallel processing, in parallel processing in here, you will lose the associativity of the numbers, the real numbers when you add them together. Okay, so adding, basically, what I'm saying is adding A plus B plus C plus D is not the same as adding A plus C plus D plus B. So therefore, it is expected that you will see the difference. You will see error, in other words. As to whether you can stand, you can tolerate that error, that's another story. And for more details, you can watch the video recording on the video recording of my previous talk on the reduction of errors in parallel computing, also available on the SharkNet YouTube channel. Okay, so this is an example of running a parallel, running a threaded code in C++, and you develop the code and test the code on C++. And the next example, okay. So, so takeaways that you have access to multi-cores on the WSL Linux, and make sure that your code works before you move on to other computers. Also, most importantly, you need to pay attention to the correctness. After you parallelize your code, or after you wrote a parallel code, always pay attention to the result. Ask yourself, can you trust the result? Or are you satisfied with the computer, the results, and which might be affected by the numerical, the rounding errors, or affected like a numerical rounding errors like this. Okay. Next example, and the next example will show you, this is a Fortran example. In this example, the code will assemble pieces of Lena image stored in different files, in individual files, and each process I'm going to have, in this case, I will have a 4x4 16 processes, and each one reads a portion of the image file, and then the master process will assemble the pieces into the whole image. That's the idea, and the code will be written in Fortran program language and supported by the underlying MPI library. The code, so each processor reads a partial image file. I will have 16 files, and each file has its own dimension, the X and the Y number of pixels, and and also a label, the number 0, 1, 2, 3 to 15, and it determines where that particular piece should be located in the assembled whole image. Okay. This is the source code that explains what the code does. First, the master process will read a config file, the total number of pixels and X and the Y, and the name of the image. That's the config file. And then each process will read a small portion of image file that contains the X and the Y pixels and depth, and then the image content itself. And the next, the master process. The master process is with the label ID 1. The master process will copy the piece from process I and into the assembled array of image. And then the master process will write this assembled image into the whole array, back to the whole image. That's what it does. Before I show that, let me just get back to the Visual Studio Code again. Now, the Visual Studio Code, there's a little icon here, and it shows an open and remote windows. I click that, and I will choose connect it to my WSL distribution, and I pick Ubuntu. The reason I'm doing this is I'm still using this Visual Studio Code to edit file, but I'm not editing a file, but I am not only editing a file on Linux, but also I want to have a development environment so that I can do things within this Visual Studio Code as well. So now, just let's wait for a bit until the connection is established. And it shows here in the starting WSL, sorry, starting the Visual Studio Code on Ubuntu. Now it's being established. Now I go to Files and the Open Files. Now I am not on Windows anymore. I am on the Linux. So this is my home directory on Ubuntu, and I want to go to net home. That's where my code is. And go to home and document, and in my folder, go to talks and go to WSL2 and the source file and the folder Lena. And I want to open the source code lena.f90. Open. Now I see the code. This is the actual Fortran source code. Okay. Now I have the source code here, and I can open a terminal. I want to open a new terminal. Now I have a terminal. I have access to my Ubuntu in WSL. Now I see my home directory. Now I want to go to the actual folder that has my files. Word, document, box, WSL, and the source code, Lena. So I'm here. So I have some files here already. I have this source file lena.f90. This is the only source file I have. Now to prepare for the run, let me show you something here. I want to open that. I want to open a file explorer again. Go to Lena. Go to Lena. And go to images. Okay. Okay. So I'm going to open the file explorer again. Okay, this shows the folder images. Now, I'm going to do. I'm going to create it the 16 pieces. So now I created 16 pieces just for this simulation, for this demo. 16 pieces, 16 files, and each one has a portion of the Lena image. Now let me just get back to just do the code, and here I'm in a command line. Now I want to compile the code. Now this Fortran code, I need to use this Fortran code uses the co-array, which facilitates the parallel processing without using MPI. The square brackets here at the end of any variable means this variable is shared among processes, and you can access any process can access shared variables very easily. You can do a copy over, or you can do a push over. Okay, and to compile this Fortran program, I'm using the coarray package compiler called a CAF, coarray, Fortran, and the lena.f90, and I give an output name called just Lena. Now, this Fortran compiler is a wrapper. It uses a GCC compiler, and also it uses the OpenMPI or MPICH compiler as well, but it hides the details. So the name for this Fortran compiler is called a CAF. Oh, it has some comments there. I need option -cpp. Okay, and then ready to run. So I run conf run, and I need a 16 16 processes. Since my host doesn't have 16 cores, so I need specify host files. And the host file, in the host file, let me just show you the host file. I'm just faking it. Host file, the host file contains a host name, a local host, and the number of slots means the number of cores. I set to 64, just faking it. I have a pretend I have a 64 cores, so I can run more than number of available cores appear to me. For example, the number of the CPU. This shows the number of CPUs I have. I only have 3, I think. That's not enough. Okay, so run cap run -16, host the files and the host, and then this executable, Lena. And once it's finished, we should see a whole image is being generated. This is a whole image, and if I click that, we should see Linux being assembled. Okay, so this is a second example. It shows a parallel parallel Fortran code. And we can run this on a Linux in WSL. Okay. The next. So the next example is this is the last example. This is the Julia code of using a distributed array. What we have here, or create a distributed array on a 2x2 Cartesian processor grid, and each process holds and stores a quarter of the array. Okay. And then we want to create a distributed array so that any process can can access and do some calculations on the distributed array, on this array stored across processes. So what we have here, this is the Julia code. The Julia code will create the block matrix matrices, the block the matrices on the diagonal, and the off block matrices off diagonal, and we go from there. Again, I'll go back to the command line, Julia. So we just run the Julia code here. Julia, I want to run 2x2 process grid in totals of 4. And the name of the file is try 3. Again, underneath, it uses the MPI library for the data communication between processes. I'm using a 4 processes on this Linux. It takes a little while to establish the communications between Julia processes. Yeah, today it takes a bit too long, but eventually it will come up. While it's calculating, let's move on. Oh, it's done. So basically, what it does is it generated a distributed array dA, and then I perform the matrix multiplication dA times dA. This is done on 4 processes on the 2x2 processor grid, and then I just verify the result using non-distributed array A and A, and the results match. Okay. All right. So lastly, let me just briefly mention that the if let's say we already have a Linux distro on Windows, we have used it. Now we want to use it, take it with us, and use it elsewhere. For example, on a cluster, how do we do that? And it is possible. So I can take this live Linux distro and copy it to the cluster. So here is the recipe of doing that. First, you need to export the live Linux using WSL export into a tarball, and then use a Docker to import that tarball into Docker as a Docker image. And then you need to save that Docker image back into a tarball that can be read by an Apptainer. And the Apptainer will build a Apptainer image from the tarball, and then you can take that Apptainer image on a cluster and then run and use it there. Before I end, let me just take 1 minute to show you how to do that. So I already have a Apptainer image and I already copied it to Nibby. And I put it in downloads. I have a file called Ubuntu CIF. This is Apptainer image. So I do module load Apptainer.
You misspelled module.
So yes, module load Apptainer. All right. So do Apptainer uh, shell and run this. Here we go. So how do I know this is my Ubuntu? Well, remember at the beginning I show you this neo-fetch thing. It shows yes, this is my Ubuntu. This is the one I copied. I packaged it up from my Windows, and I have a GCC 13. And let me see if I can go to my home directory. Oh, sorry, go to talks and go to, yes, I have there, and go to source because I copied the files out to Nibby. Go to sum, and then I just compile the file. and X sum. And give a name and link against thread building block. All right, so it's ready to run. Now, by default, it will use all the cores available on this on the node, and we'll see what happens. Now, it shows sequential submission takes 0.4, and the parallel submission took about 1/10. I'm not sure how many cores are available on the
16.
16. Okay,
Or sorry, there's 32 there. I think there's 32 there. It's
am
16
I
or
able to
30.
use the 16 all the 32 cores on the logging node, or am I
Yes,
limited?
on the login node, yes, there might be some oversubscription, but
Okay,
I think all processes are limited to 16 gigabytes total that you're running, and you can use up to the number of cores that appears in your session, and I think it's 32.
okay, all right. But the most important thing is there are two things. One, we do see a speed up. We do see the reduction of the execution time by using a parallel version using threads. And the second thing is we see the results differ. Again, as I pointed out, because the numerical rounding effect. Okay, so I think I should stop here. Um, here's a list of references.